Welcome, everyone. Today, we're very happy to have Yuhsin, our relative neighbor from Notre Dame.
Are you Catholic, Yuhsin? No.
Sorry?
You're not Catholic. Are you Catholic?
No, hold on. That's what you asked that before I started recording.
I don't think you're supposed to ask that. You really do your training well.
No, yes. I was curious because usually,
not.
How do you feel?
Yeah.
You figure that out?
usually you have to be Catholic.
No, I don't.
Good.
Maybe I'm in trouble that I don't know. I will figure that out.
Good. Okay. Well, so we're happy to have a talk either on.
Oh, this is recorded?
Well, the talk is either on religion or on cosmology. We'll see which one.
Yes.
Thank you.
Okay, thank you everyone. Yeah, as Seth was saying, I'm from Notre Dame and it's not far from here. So really, hopefully I can come here more often and to chat more physics with you. For today, I'm going to tell you something that I'm quite interested in these days. It will be like a talk about some cosmological study, but I'm going to tell you the story more from a collider physicist point of view. Okay, it's a different way to try to look for signals on the CMB map. So first of all, the whole story I'm going to tell you contains the thing that we put out in our first paper more than a year ago with these great collaborators here. But I will also give you some new stuff that we do after that, which is basically some analysis, the more careful analysis we do using the some convolutional neural network process to dig out the signal that I'm going to describe about, and also just make some of our old calculations more precise. So I definitely have to say that in this follow-up project, we have a fantastic student at Notre Dame, Kim, who basically helped me to set up all the convolutional neural network studies. And just to make sure we are doing things correct and not making like stupid mistakes. So we also invite a real cosmologist, Boris Mushmir, and who is an expert on identifying this more localized objects on the CMB map. So he is also helping us on this project. And hopefully we can put the paper out in a few weeks, and I'm really spending time writing it. Okay, so the goal of this study and then the story today is that we are trying to probe a very, very heavy particles. We just think like a particle physicist, using the inflation dynamics and then also the imprint of the new particle on the cosmological signals. It would be the CMB in this talk. So the particle detector would be the CMB's map, and the collider experiment to produce the particle would be the inflationary error of the universe. So I think in this crowd, I probably don't need to go to all the basic of the CMB. So I will just leave this here. But one thing I want to remind you is that usually when you hear people talking about the CMB study or large-scale study using the large-scale structure of the universe, the way that we track the physics from that CMB fluctuation map is to calculate the endpoint correlation functions. So we were calculating 2-point correlation functions of the temperature fluctuation, or 3-point or even higher endpoint functions, so that if there are some physics hidden in the early universe, is going to change the property of all the fluctuation, the behavioral fluctuation of the temperature, so that we can learn about the new physics from here.
So what is that feature at L equal 20?
L equals 20, this one?
No, 20.
Oh, this one?
Yes, that.
You mean like this?
Yeah, since you want to learn something, what is it?
That's right. Yeah. So of course, when we learn something, we also need enough statistics. I agree.
But that looks pretty prominent.
Oh, you mean this one?
Yeah, yeah.
Oh, actually, people do build phenomenological models trying to explain this feature.
That
some
feature?
of the feature.
Okay.
So it's similar, like they have toy models.
Somehow this plot doesn't have the cosmic variance error bars on it.
No, I think it's in it.
Oh, it's include those error
Yeah,
bars.
it's included.
I see. So because usually there's some band just showing you the where the
it's a blocked by my words.
yeah,
here.
because once you see that band, it will be obvious that these lower multiple deviations are not.
Right. There are error bar you can compare.
Well,
and you see them. Yeah.
Okay, fine. You think that is an error problem?
I think it's some.
That is a feature that is always there, right? So it's very strange. You
Well,
go to previous.
We always just observe the same
Yeah.
universe.
So
Okay,
this is
okay.
now going to change. And the error bar is dominated by cosmic variance.
Okay, it
so
looks pretty picky to me.
You should ask Wayne about it.
That's
Yeah.
how people build a non-standard inflation model.
Exactly.
Non-standard inflation.
So
model.
people do try to build a model to explain the feature.
Okay, very good. But just,
Yeah.
I was not trying to argue. It's just always strikes to me that
Yeah. So it's
there is something there.
yeah.
Okay, thank you. Sorry.
Yeah. Right, but okay. To show you this plot, I just want to say that it actually makes sense to study the power spectrum or endpoint correlation functions to look for to general physics, because if you look at the fluctuation of the map, the size of fluctuation is pretty much scale invariant. Okay, so it definitely makes sense to think about statistics of the fluctuation and then get physics from there. But that's not always true, okay? Actually, for the example I'm going to tell you is actually the power spectrum analysis won't be the best tool to use to study the signal. You actually want to look for more localized objects, but I'm going to come back to this point soon. But again, just come to the thing that we talk about, trying to probe very heavy particles using inflation. And there's already a very active research area about cosmological collider physics, and we also have many experts here that already talk about using the particle production during inflation to study the possible existence of the new particles that couples to the inflaton field. Okay. The physics I'm going to discuss today will be related to this physics about how to produce these particles. But the idea is that during the inflation, because we are in the so-called de Sitter space-time, so when you define the vacuum state actually keeps changing with time. So when the vacuum can change, there will be a thing called the non-adiabatic particle production will happen. I will describe a bit of that later. And that can have a chance to produce some new particles on shell. And when these particles couples to the inflaton fluctuation, it can generate a non-trivial fluctuation of the inflaton, like this non-Gaussian like a bispectrum, so that we don't expect it to be there in the standard cosmological model. So if we get to see this, then we have a chance to measure all the different properties of this heavy particle. So when considering this physics, because I just said that we produce a particle by the changing of the vacuum and everything, and that energy scale associated to the Hubble scale during the inflation, because that says that the changing of the time scale is a Hubble. So it's not surprised that when you calculate this kind of corrections, your final result will be a carrier suppression, more like a thermal suppression kind of thing. When the particle you're interested in is much higher than the Hubble scale, then you get the exponential suppression, so you won't be able to really go to a very high mass. But even so, the Hubble scale can easily be like 10 to the 13 GeV, then you still have a very good chance to produce something heavy.
Where does the pi come from?
Yeah, so I'm also trying to find a good argument of pi, but it's just when you do the calculation, it usually shows up.
Usually shows up. Okay.
Yeah, and even for the slight different calculation, I'm going to show you, it also shows up. Yeah. But please let me know. I mean, I know there are experts here.
Where does the pi come from?
Bakery.
The fluctuation is h over 2 pi.
H over 2 pi. Okay. Ah,
It's just I don't know. It's I guess you can absorb it into some definition of
Definition of H.
So for the Sitter temperature.
Yeah.
Sitter temperature as a part.
Yeah, I'm not surprised.
That's a part.
There is some kind of
Okay.
I don't know what it is.
Not this an intuitive. Okay.
I don't have a deep insight.
Yeah.
Okay.
Okay, so again, our goal is to ask, but I'm not happy just with this mass. I want to push the mass to be even much higher than the Hubble scale. Then is it possible to do that? And if that's the case, then how would the signal look like in that case? So this would be the case we focus on in this talk, thinking about if I want to produce a particle mass much heavier than Hubble. And one thing you can already guess what will happen is that in that case, you don't get to produce these particles everywhere in the universe during inflation. You have a much more suppressed probability. So whatever feature you generate would be more like a localized object on the CMB sky today. And the other thing that we will have is that if you really have a chance to generate such a heavy particle because it has a large mass, it can locally change the curvature perturbation in that region. So that may have a chance to leave a signal on the CMB map. Okay. So this is just a cartoon picture just to show the idea, but later I will give you a more careful calculation of how the signal will look like. So this leads to the signal I want to talk about today, which is a pairly produced hotspot signals on the CMB map from this very heavy particle production. In this case, as you can imagine, like if I only have a few of those on the whole sky, the power spectrum, correction to a power spectrum would be very small. And you really need to use some template search to look for this localized object on the sky. So the way to look for do the CMB search will be very different. Okay. So the structure of the talk is very simple. I will use probably 2/3 of the time just to discuss this physics. How do I produce this heavy particle and how does it end up leave an imprint on the CMB? Okay. But then after that, I'm going to give you some more like a simplified analysis using the neural network just to show how plausible it is we can get the signal. Okay, so this just shows the timeline. We are going to produce this heavy particle during inflation. And after that, the mass of the particle is to locally change the curvature perturbation, and then that perturbation will leave the horizon, got frozen outside the horizon. So even after that, the particle decay or stay there, it doesn't matter. It would be the change of the curvature perturbation of that Hubble patch when they enter the horizon again, they will change the CMB image, and then we get to see the signal today. So that's the process. Okay, so for the particle production, it's like I want to see the production of these new particles. So the physics I'm going to tell you actually doesn't really matter if it's a scalar or fermion or like some more detailed property of the heavy particle. But let me just write down one example that I can actually do the calculation and tell you how the signal looks like. So let's just consider there's a scalar particle that has a potential and carries a mass term, and let's say the mass of the sigma somehow depends on the inflaton wave. Let's just make the assumption. So while inflaton is rolling and changing its wave, at some point there can be some local minimum that happens that the sigma will get a slightly smaller mass around a certain point. Let me just call that time as some eta star as conformal time.
So this happens, the eta star is in the era where the CMB modes are being made.
Yes, so the eta star needs to be in the range of the.
And this does not generate observable back reactions.
I will talk about the bounds on the not destroying the the inflation.
Because you wanted to make it the light during the CMB era.
You mean?
Is that what you wanted to do? And you want to make the particle light?
I don't need it to be too light.
Yeah.
I just want it to be mainly produced at the one.
But lighter than it is.
or comparable to the energy scale of the inflaton. Yeah, that's right. Okay, so because of this, for now, I'm going to assume that the particle production will mainly happens here, because otherwise there will be exponential suppression because mass is heavy. And then everything I'm doing the calculation, I can basically just do a perturbation along this time. Okay. And here again, this is just an example. You can have a different mass and then do the similar analysis. Let me just assume that the mass of the scalar particle carries this phi dependence, and then phi rose to a certain value, I get the minimum mass. Okay. So that's just a setup. And you can do this for fermion only, also. Okay. So one important thing here is this coupling G. So definitely my final result will depend on the size of the G, which is the coupling between the inflaton and my scalar field. Okay, so with that, I can just write down my equation of motion of the scalar field in the conformal time. It's just one way to parameterize the time. And then it will have this form, and then carries the mass term that is time dependent. One thing I need to say is that even without this additional inflaton dependent mass, during the inflation, the particle mass will change with time. And that's the thing I say in the beginning. The mass is changing, so the vacuum state is changing, and that's how all this particle production is happening. But here, in this case, my mass will also carry a time dependence. And I can just redefine the variable, and then this will just show up as a simple harmonic oscillator equation with a time varying frequency. Okay. So that's the equation of motion of the scalar field. Okay. For the production of the particle, I cannot just do a calculation like doing the Feynman rule calculation as in the Collider experiment, because I don't even have a well-defined, like a fixed mass and the usual Feynman diagram to use. So the way we should think about the particle production is the change of the vacuum and using the picture of the so-called Bogoliubov transformation. For people who haven't seen this, the idea is very simple. I mean, you should be able to kind of roughly understand what's going on, which is that since the equation of motion gives you a time-dependent mass term, so let's say in the initial time, I have a given mass, and I solve all my the wave function of the solution, I get some ground state. So this will be vacuum in the beginning. But the later time, because my mass changes, so I have a new ground state and new excited states. And when you're trying to match the initial ground state and the later time state defined by the new vacuum, the initial ground state will now becomes a superposition of not only the new ground state, but also the excited states. So this will just be meaning that you now have particles being produced. And there is really the calculation that you can do. So basically, remember when we do the A and A dagger quantization, there is a field solution for the equation of motion we need to put in. And the only thing I'm doing is I found a solution in the early time, and I found a solution in the late time. And then I just match the frequency mode, and then just to see what's the different sign of the frequency mode now being generated. Because that will correspond to, if I'm in the new raising and lowering operators, there will be the A and A dagger mixing coming from my initial time vacuum. So because of this, if I calculate the number density, average number density of the particle at a later time, I put the B and B dagger, and looking at Heisenberg's picture, so I'm looking at the vacuum from the initial time, the result will not be zero because the B dagger contains A and B contains the A dagger, so I will end up getting a non-zero result. And this is just give me the number density of the particle that I can produce. I do have backup slides for the real calculation, but just for people who are interested, I can show you later. But this is basically the idea. So once I get that number density, and I multiply the number density to the volume that I'm interested in, which is the certain volume, like a shell with some finite thickness around the less current surface, I can calculate the total number of particles that would be there and change my CMB signal. And the total number on the sky that will change the CMB will have this expression, where the exponential is just similar to the exponential we were talking about before, that having a suppression. But in this case, instead of having a mass divided by Hubble, now in this case, because the inflaton helped me to change the mass, so the comparison becomes the mass, the bare mass of the particle to the inflaton kinetic energy and times the coupling. Okay. And then this is just a volume factor, okay, from this.
Why is
Yes.
Sorry, the downstairs G times 5?
Yeah, G times phi dot. Yeah, because for the mass term, when you calculate the mass changing rate, because that relates to how non-adiabatic the process is. So you do that linear expansion in time, you get the G times the phi dot. Yeah, the mass changing is the delta phi times G, and then the rate is, yeah. Okay. Just to give you an example, you can ignore this equations here. If I'm considering a case when the coupling between the inflaton and my scalar is 2, just putting a coupling, and considering the bare mass to be 200 times higher than the Hubble, or the answer is about 3 times larger than phi dot. One thing is that the reason why I know what the phi dot value is because from the CMB measurement, I know how quickly the inflaton needs to roll. So this is about like a 60 times of the HI for the square root of phi dot, but we know this. And assuming that I'm thinking about the production happens at a certain size, 100 mega per second, this is basically you chop the sky into 500 by 500 pieces. There's some square root pi, 4 pi put here. And then in this case, in the whole sky, we can produce about 30 pairs of the scalar particles in the sky.
But why does it have to be a pair production?
Yes, I haven't mentioned that. But also here, I won't show the detail, but the thing is that this just comes from the momentum conservation. So when you write all those A and A dagger, you will see that the spatial momentum needs to contract with each other and then get there will be some delta function of the spatial momentum need to conserve. So because of the momentum conservation, they need to be produced in pairs.
Why can't you recoil off the inflaton background?
Yeah, because the way to think about the inflaton is that it just changes the vacuum in the background. It can be that if we include the more careful calculation of the back reaction, there may be higher order terms. I can balance the momentum. But just from the leading order calculation, when you just change the background and just pump out the pair of particles from vacuum, they need to conserve the momentum. Yeah. Okay. Any questions so far? Okay, but it will turn into more margin. Okay. So, yes.
Why you only focus on CMB?
Yeah. So actually, I'm now also trying to think about the large scale structure, but I just haven't got time to that. Yeah, and CMB is the thing that I can more easily simulate. Yeah. Okay. So there will be back reaction constraints, as Leontel were asking. I don't want to change the equation of motion of inflaton too much. I also want to extract too much energy in producing heavy particles. So both of this will give me an upper bound on the number of particles I can produce. So I'm not going to get into details here, but that bound is actually pretty weak. Okay, so for the whole sky, even if you produce like roughly million, you will only get to saturate that bound to change the inflation dynamics. However, of course, there's another issue, which is that now I put in a new coupling between the scalar and the inflaton. There's radiative correction. I need to make sure the inflaton potential is flat. And that one will definitely require additional UV completion. There are examples that have been given in a similar study from Raphael's paper a few years ago, and they just super symmetrized the system.
It's not just because I think if you make it a flat at the beginning or later, but there is some local feature, right? Because the field you integrate out to generating to correct the inflaton potential, that field becomes lighter during the CMB epoch. Right? There is some local thing that it's not like I can imagine that there's some UV completion that make sure that
So you mean the sigma field?
Yeah, sigma field. I'm imagining you to think about the inflaton. You can integrate out the sigma, like write down. Or maybe just write down the Coleman-Weinberg potential for phi, and it all depends on the sigma mass. Right, the sigma mass gets lighter during the inflation, and there should be some local feature being generated.
Right.
On the inflaton.
Right.
Potential.
One thing I should say that even though I'm thinking about that, it becomes lighter, but it's still way heavier than the.
It's heavier than H.
It's heavier than H.
Yeah, but may not be. It's actually may not be heavier than the 1/4 of V.
Right. So.
So you are not that much heavier than H, right? You are 100 times.
100 times, yeah. So at least for the toy model study we had before, we are aiming for even in that minimum, that would be, still maybe a factor of 2 or 3 times heavier than the square root of phi.
Okay.
Phi dot.
Yes,
but it's comparable.
But I think I'm worried about the local feature that you're going to correct. Just correct V, and it's not I think it's different from when you're producing particle, you slow down the field and so on. That's a different effect, right?
Right.
That's like an effective friction.
Right. So there is this effect, and the other thing is just directly you look at your inflaton potential. You just want to make sure whatever term that you have here is way smaller than the kinetic energy of the inflaton, just from the equation of motion, and that will also give you a sense of upper bound.
Okay.
But I'm not totally sure if it's exactly the same as you say integrating all the field and generating the feature. That I need to think more about. Here we just compare.
It's better. You better be able to integrate it out. Otherwise, it's a multi-field inflation. So then you have temporarily light field. That's not what you want.
Yeah.
Right. So then. Anyways.
Okay. Right. So, but for the number we'll be talking about is way smaller than this bounds. So I briefly mentioned about the pairs, and then the separation of the particle is actually can go all the way from comparable to the size of the horizon. So we just simply assume it can randomly pop out with a uniform distributed separation in the Hubble patch. Okay. So let me just move on. So let's say, okay, now I can parallelly produce these particles, and what does it do on the CMB? So the way that it leaves the imprint on the CMB is that the existence of the mass is going to change the curvature perturbation around the mass. And when I use the word curvature perturbation, you can just think about some combination of the photon energy perturbation and the gravity, because they need to put together to give you a temperature fluctuation. The only thing I want to emphasize here is that, let's say you first produce a particle, then the mass changes the curvature perturbation. When you first produce it, you will have some value of the mass. But then this initial curvature perturbation will leave the horizon, and then this particle mass will change a little bit, right? Because the inflaton keeps rolling, and the mass of the particle now becomes a bit heavier, and then this will induce a slightly different curvature perturbation at the next instant of time. So, and then this will leave horizon, and then you just repeat the process again. So every time you generate a slightly different curvature perturbation, and in the end, when you look at the sky in the position space, you will have a profile of the curvature perturbation as a function of the radius. And you can calculate the profile. Again, I leave more details in the backup slides. You can calculate the profile, and the final result, it's not a surprise, will be proportional to the coupling you have between the heavy particle and the inflaton. And then it will take this logarithmic profile for the radius. Okay? So when the radius is the horizon size, you get 0. And when you move to this more inner region, you get the logarithmic enhancement of the curvature perturbation. And then this term is just some combination give you the usual primordial perturbation you measure from the CMB. So this is the standard. So this is the actual profile. One thing I want to say is that this logarithmic profile is pretty robust, okay? Because this simply comes from if I can do a linear perturbation in time for the production and calculate the change of the mass, the physical time will look like have this logarithmic dependence on the conformal time. Okay? So this is really just coming from the inflation dynamics. Okay? So this is useful because it tells us if I later design a search to look for object with this profile, those things are pretty useful because as long as you can describe the particle production process around 1 instant of time, then you can do a linear expansion in time. Your initial curvature perturbation will look like this. Okay? So it only depends on what's the horizon size that you have. It doesn't really depend on what kind of particles interaction you have. Okay, so that's one good thing of this. And now there's an interesting question, which is that maybe you heard what I was saying in the beginning, that I said purely produce hotspot signals. I didn't say purely produce cold spot signals. And the question is, how do I know it's a hotspot or a cold spot? Okay. It's actually not that trivial. And I have to say that when I get into all this pairwise hotspot physics study, I was motivated by one paper from Juan Maldacena, who just proposed there can be an example that you purely produce this signal in the sky, and then you can do some crazy Bell's inequality experiment. You just imagine that one can do that. The idea is pretty crazy, but it's a very nice, the craziness is very nice and interesting. But I got interested into the phenomenology aspect of it, how would the hotspot look like. So you can find one sentence in Juan's paper that at some point he was saying that basically what he said, I don't care if it's a hot or cold spot, how does it look like in the end? I'm just going to code this as a hotspot. And he put a footnote inside the paper by saying that can change. My scenario is he probably got an email from these people and saying, oh, what you said is actually a cold spot, but not hot spot. Okay. But for his purpose, he doesn't need to care. So then the question is that, what's the answer? Is it pairwise hot spot or a cold spot? So there's some interesting cosmology here, which is that if you use the size of the curvature perturbation, because you can imagine when I produce a particle, it generates a gravitational wave, right, in the sky. Because of the so-called subswolf effect, when photon around the particle trying to climb up, it will lose energy. So if you just look at the initial curvature perturbation, you actually expect to get a cold spot from the CMB map. But in order to really know in the end is hard spot and cold spot, you need to include all the sub-horizon physics thing, because we know that in the CMB, it's not only about the initial condition. Once the initial condition comes in, you need to worry about how does the photon and the baryon or the scattering with each other and having all these oscillation calculations. So you actually need to take those into account. So the way to do this is very straightforward. You take the profile that I gave you in position space, do a Fourier transform, and for each of the K mode, we know from the standard cosmology how to calculate the evolution of the photon and the gravity perturbation for each mode, and you put them back into position space and project on the 2D less scattering surface. So if you do that calculation, for the size of the horizon we consider, and also Juan was using as an example, we actually get the hotspot in the end. So Juan was right, even though he didn't do any calculation. And then you can really just calculate the profile, and it's not exactly always hotspot. You actually have some oscillating profile because of the baryon acoustic oscillation physics. But if you look at the angular profile in the sky, the pairly produced hotspot will look like these images, and depending on what's the horizon size you have. Again, the profile itself is very robust, but the overall size of the temperature will be proportional to the coupling G. And does that mean those people who emailed him, well, that's not true, I just guessed, were they wrong? Because they tried to argue it would be cold spot. Actually, they are not wrong, because for those papers, they are trying to look for a much bigger horizon size. They are trying to explain the cold spot that we see on the CMB. So if you do this profile calculation, this is what we did. Just look at the central value of the temperature. If you look at large enough horizon size, you do get a negative temperature. Just simply because the initial condition give a negative temperature, and then for this size, you haven't entered the horizon for long enough to be reprocessed by all those acoustic oscillation physics. And in this follow-up work I mentioned, hopefully we can put out the paper soon. We also consider a more realistic case that the particles can be slightly away, like outside of inside of the less scattering surface from us. So that will also changes how the image looks like on the CMB map. There are some interesting things relating to the feature of this thing and how the neural network can pick up the signal, but I will just leave that for the.
Sorry, what do you mean by
Yes.
particles are away from last scattering surface?
Yeah, so because when we think about this particle production, we should really think about in 3-dimensional. Right? So in the whole space, there can be particles pumping out here and there in 3-dimension. But the thing that will be more relevant to the CMB is only the one that close to the last scattering surface.
But that surface is a 3D space.
Yeah, the surface is in the 3D space. Yeah, it's a 2D surface on a 3D space, but I can imagine if I have a particle that will produce and later expand, and then shows up, I have a heavy particle here. I can locally change the potential around this region. So this is observer, and I'm looking back to the CMB surface.
The particle was produced way early, right?
Oh, right. The particle is not only important. I just mean that this chunk of the horizon in 3D has been distorted. But the photon still propagating from there to here. So if I have something not exactly on the surface, but slightly away, I can also change the gravitational potential on this 2D surface. So in principle, I can randomly distribute this. Yeah, and then also depending on the horizon size, the image will look differently. look different. And also, when you move in and out, it's actually not always symmetric, because this relates to certain modes you are looking at got more corrections from later time gravity effect and stuff. So you need to take into all those things account. So the profile may be quite subtle, but again, if you give me a horizon size, I can basically just tell you all the answer, okay? Even though the profile is a bit subtle. Okay. So now, for the last part of the thing, like, let's talk about what's the possibility of digging out the signal from the CMB map. So even if you don't care about all those theoretical motivation and particle production, here I just give you a simple question, which is that if I have this signal that I know it should look like this for different size of the horizon, the different horizon size, I want to put this signal on some CMB background. And what's the chance I can identify the signal with certain brightness of the signal?
It's a machine learning.
Sorry?
No.
Yeah, it's like a machine learning. Exactly. That's the.
I can see a few.
You are a good machine.
Yeah.
Yes. Yeah, I actually tried quite hard to, because this is actually for a pretty large coupling, and then, yeah, still it's hard. So just a little bit detail, we use the package. I can simulate the CMB background following the power spectrum that we got fitted very well from the Planck observation. And for a given size number of the signal and given horizon size of coupling, I can just inject certain number of those and then just see how well we can do. Just for the different signal, okay? Of course, to really do the thing on the real map of our universe, that's eventually the thing I want to do. There will be other background to consider. There will be instrumental noise, just from the Planck looking at the sky, there was some noise that we, in principle, need to consider, but at least for the future we are looking at now, we can kind of be just assuming the noise is small. The real problem is the foreground, because even if you look at the image from Planck directly, when Planck just take an image of the sky, you have lots of like unwanted things that you don't want, which doesn't come from the CMB. You have lots of compact objects, the galaxies, galaxy clusters, and dots, and all of those. So we need to subtract all of those in order to do the search. Yeah. So we actually have been talking to several cosmologists, but somehow it makes sense, whoever have been working on this, look for localized objects on the CMB map, they are very confident that we can subtract all this localized stuff well enough. But there are also some hope that we can indeed do well, because first of all, these localized objects have a very different frequency spectrum comparing to the CMB signal. So like Planck has a different channel of the frequency probe that we can do. So that's how they used to identify all these compact objects. So they can subtract those. And also galaxies usually have certain shape that can look very differently from the signal we are looking at. So there is a chance, even if there are galaxies remain there, we can distinguish that from the signal. But for the analysis that we are doing, and I will describe, we are going to assume the best scenario that we can have. Okay, so the thing I'm going to show you is what kind of the ultimate thing that we can do. To consider that the only background is the primordial CMB fluctuation. Okay. So in that case, we want to answer, in the end, how heavy the particle I can probe for a given size of the coupling. And this will be the indistinguishable background. So even though Carlos directly say, oh, you should do machine learning, but if you tell the story to the cosmologists, they will say, why bother machine learning? You just do a match filter analysis. Like we have lots of filter templates being used for the astrophysical searches. And also, if you ask a good student to do the machine learning projects, there's a very high chance they will just leave the field. Like, so why do I even want to take the risk of doing things on the CMN, the Convolutional Neural Network? And in the end, it's just that it's easier, it's more flexible for you to identify the signal. Because the traditional match filter is very good if you have a spherical symmetric signal and with a well-defined template. But for the signal we're looking at, we'll have some randomness of the signal, like moving around and then different separation. And also the signal is not spherical. Okay. So in principle, you can design a match filter to do that. But if you just let the network to develop its own template and extract the signal, that would be actually simpler thing to do. Okay. But even so, we still studied some examples, some simplified version of the signal, and then just compare the CNN and match filter analysis. And in many of those, we get a similar result. So the machine learning thing I present is not crazy, but some of the example is also a bit hard to really do an apple-to-apple comparison because there are statistics. How do you design the best search for the different search strategy? That's a bit subtle. So that part we're still trying to understand later. I'm going to claim that I don't have time to explain the detail of a convolutional neural network, because I don't know any details of this. For people who know how to do this, this is the structure of the network.
It's a package you can download.
Yes. And it feels like the main work is like how to collect the training data and then store the file and all that. Yeah. But for people who want to know more, I can give you some keywords later. Okay. But the idea is that we design a neural network, we generate 160,000 images with and without the signal in it, and then just let the network to learn. And then you can get, probably it's a bit too small, but what I'm showing you here is like for different coupling, you can calculate what's the signal capture rate and the background faking rate, and then you can use this for the actual study. So this is just one example that if I just look at what the image got stored in the, I believe the third layer of this convolutional network, and you can begin to see that if this is a background, this would be what you get. And if this is a background plus the signal, you will see that machine trying to highlight some of the feature of the signals after you run this convolution layer for a few times. And you begin to see a bit of signal here. And then you will keep going and then ends up having a result. So the way that we do the search, just a very simple description, is that we train the network to be able to look at the sky into some smaller size patches. And the output will be the probability of seeing a signal here or not. So in this image, we already, I haven't included the CMB map because I just want to give you an idea. So you can imagine the signal plus the simulated CMB map for the bigger chunk of the sky, and I'm going to slide this window. And for each of them, I will get a probability of how likely there's a signal stored in certain region. And then I can just do some clustering on the probability map, and then just veto some of the signals if there are too few pixels that is relevant. And then I can end up counting the number of signals that survives. And then also the fake signal, like this one, that just pump out from the temperature fluctuation in the background. So after doing all of this, I can just do some statistics because I know how big the sky is, how likely I get to keep my signal, and then how likely I'll get a fake background. So this will allow me to calculate some upper bounds on the number of the scalar particles I can have in the whole sky. And this will be the number. Okay, for some of the signal, when the feature is more distinct, the search can actually be very good, okay, because it looks very differently from the background temperature fluctuation. But for the signal like this, with just with the one dot in the center, basically, for the signal, will look more like this. Even though the temperature of the central spot is higher, so in principle, we would think it's easier to see, but because the feature can be easily faked by just randomly you have a hotspot that pumps out from the background. So the search is actually worse. Okay, so for this one, even though it's dimmer, but because it has certain feature, it just somehow the analysis is better. Okay. But this is kind of the problem of the CNN analysis. In the end, I can only roughly tell you with what feature it will help for the CNN search, but I cannot exactly just show you or prove you. Like that's actually the thing that the machine we're looking at.
You need to trust the machine.
Yeah, somehow it is. So that's why also we are trying to compare some of the result to the match field, the traditional match filter analysis, just to make sure it's not too off. Okay. Sorry, you have a question?
Yeah, maybe I might have gotten lost, but it doesn't seem like your search has taken advantage of the fact that these always come in pairs, or has it?
That's actually a good question. So we actually did that test. If you have a signal that is just localized one dot, we compare the search with and without a pair, and definitely the pair will help you. But for the signal that even for one hotspot that already looks like a ring with a dot in the center, for that one it doesn't matter that much.
Sure, okay, but in case of, presumably a pair is much harder to fake. I mean,
Right.
because they should look the same, right?
You will think so, but actually when you look at the probability distribution of the background, in position space, the CMB fluctuation is about 100 microkelvin. So that's like a 10 to minus 3 level fluctuation. So it's actually much larger than the usual 10 to minus 5 people talk about. Because people usually talk about for each K mode, it's 10 to minus 5, but when you sum them. So you can easily have a plateau, like a continent, island, mountain get together. The place you will have one fake hotspot has a much higher chance to have another fake hotspot show up at the nearby location. So we checked some of the statistics and realized it's not hard for the background to fake the signal. Yeah. So if you only do a search using one pixel, the center of the signal, it's actually not good. You actually really need the profile. Yeah.
Thank you.
Okay. Anyway, so I'm basically done. So what I'm going to do next is for this number in the sky, I know what's the number density, and I can use the thing I described before to translate that into the mass, the bare mass of the heavy scalar particle, comparing to the Hubble or comparing to the inflaton scale. So this is basically the factor that show up on the exponential separation, the square root of that factor. Okay. So if I'm kind of trick you by saying that, oh, this is how well we can do when comparing to the Hubble, this 100 times larger than Hubble. What I really do is that I'm not actually using the Hubble as an energy source to produce a particle. I'm actually stealing the energy from the axion to produce the particle. So in the end, I can produce the heavy. I have a chance to probe heavy particles of order 3 or 4 times heavier than this the scale, roughly. Okay. well, order 1 factor, because there's a square root pi there. And then this would be roughly how the bound will look like. And for people who are interested in, because in the beginning I said the power spectrum search will have no use here, but I've never really shown you any example. So let's just take this example, and it turns out the worst search would be for this larger horizon size with a smallest coupling we are using. So you can allow to have lots of those in the sky. And one thing I can do is that I can just literally just throw those things in the sky, even assume they're on the less scattering surface. So have a maximum change of the power spectrum. And I can calculate what's the correction to the meta power spectrum. And this green curve here would be the kind of the deviation from the usual Gaussian predicted spectrum. It's well within the error bar. If you calculate chi-square, delta chi-square is very small. So basically it tells you that at least for the temperature perturbation power spectrum, there's no way that we will be sensitive to the signal. One can kind of consider the higher endpoint function on Gaussianity, but for those you really need to redesign your template for those. And there are actually studies on those, and the bound doesn't seem that good. So just let me conclude. So in the end, the point I'm trying to make is that if you have a heavy particle capturing inflaton, so the mass can change in time, there's a chance that you can just pair produce this particle and they will leave an imprint on the CMB. If they are very heavy, it would be localized object or not just showing up everywhere. And the signal is well predicted and really having a pretty generic profile in the sky. Power spectrum search is not good, but you can think about the different template search or the match filter or the CNN search to dig out the signal. There are many more things to think about. How about the large scale structure signals? How about the effect of the foreground? And one thing I'm actually also very interesting is that even though I tell you if particle is light, you change the sky everywhere. If the particle is heavy, you have a localized object. But how about the transition region? Okay. If I keep slowly reducing my particle, there will be a time it will be between localized object and correction to endpoint function. So for all of those things that would be worth exploring more. But then just happy holidays, and then thank you everyone.
Any further questions for Yuhsin? I can start. Question. Have you thought about interpreting these constraints in particular well-motivated particle physics models? I mean, well, you've written down a Lagrangian or what have you, but like, would this necessarily be a signature of relaxion physics or something like that?
Yeah, I have to say I haven't thought about this yet, but
it's very general as you've shown.
Relaxion has no inflation model.
It doesn't. Don't some people want to do it during inflation?
Never succeeded.
Oh, okay. One more constraint to say it doesn't work.
Yeah, and also I do assume a mass term here, and then this would be on some mass term on top of that. I have additional correction. So if it's oh, sorry. One thing I should say, of course, one way to write down the model is you can also have the periodic potential. So for all the discussion, we are just looking at one period. So you can have your sigma field embedded into some sine function.
Interesting.
So that's actually the thing that I'm thinking about doing, but I need to push the student to do that. You can imagine you have a periodic potential. So in the whole CMB sky, you have some discretized horizon size that you can have a signal particle production. I'm pretty confident that the machine can also pick that up. And that's actually a better model to think about because you just don't really focus on one scale, you actually can have a larger range of the scale that you can produce the particles. But just for this physics as a proof of principle kind of study, we only consider one minimum. So in the Raphael paper that I briefly mentioned, they did a similar study, but for the endpoint function study, and I think it doesn't work very well. But the physics is similar, and they do consider the periodic potential. Yeah.
Well, I have a related question, but so right now I assume that you are not detecting any feature that will point towards. But when do we expect this to succeed? So what kind of accuracy? CMB, the new CMB.
Yeah, so it's more like because for now I don't have a very good target for what's the mass in the coupling. So this would be more like a simplified model study and trying to push the mass and lower the coupling. And we can already do a search, of course, but the constraint is actually because I haven't get to study the foreground and the map. So that I actually need some help. So I need to consult more expert on how to clean up the map and do a real thing. But in principle, we can just look at the Planck map and then can set a bound. And
then something that is only indirectly related to your seminar, you mentioned this paper of Juan.
All right.
What was the Bell inequalities that he was trying to...
Right, so detail I don't quite remember, but he was trying to say that if you have two separated hotspots, and each of them, the temperature of the spot somehow related to the field of some axion-like particle, like a field. So the field value itself will give you one measurement, and also the background curvature fluctuation from the cosmology will also give you another measurement. And you can compare this measurements like a Bell's inequality experiment to see if the CMB fluctuation is quantum or classic or thermal.
I see.
So that's the idea. It's very cool, but of course you do need that existing field, but it's an interesting thought. Yeah.
Okay, go.
Yeah, I just wonder some more details on your search.
Yeah.
So you haven't tried put the thin on the Planck?
No, because I'm really trying to learn what's the proper way to do that. Because even though I say we have a chance to subtract all the compact objects, but even if Planck is doing that, you will see the temperature profile is not exactly black body. So meaning that you still get some pollution from this compact object. So with the imperfect subtraction, I'm still trying to learn how do we take that into account and then just...
Why not just mask all this point source region out and look at the risk sky?
But if the point source is too dim, I don't even know if I should map out here or there, right?
Yeah.
So for the current search, we're already using roughly only 50%. Yeah, maybe if we map out more using 30-40% of the sky, that would be good. That will not change the bound I show you too much. So in principle, if I know where to map out, then I can do that. And also, I also want to see, like, even if I have a cluster or a galaxy, because we have a very well predicted signal, that's a good thing for the profile. And maybe there's a chance the network can just say, this is not a signal, this is a foreground. But I need to be able to, the main thing is I don't know how to generate training data with some simulation of the foreground. If I know how to do that, then I can do it. Maybe I can just put in something by hand and just give it a try.
Yeah. Another question is, seems to you first train your neural network on small patch of sky.
All right.
Why not the whole patch? Like,
yeah, it's just it takes too much time to generate 100,000 images if it's too big. So many of these constraints are not real constraints; they are just our ability and the computing source to generate the images. Yeah. So I didn't say, but for the thing that we did for all this training, we do the roughly 20 by 20 degree, and we scan that trend network across the sky. If we want to do that 10 times larger, then yeah, it would take much longer time to generate data. There must be people who are much better on all these things can do this more efficiently, but
Yeah, my feeling is like if you do much filter, it will be much easier. Like
right.
you can pick up a few parameter choice you have and then build the match filter, and then you just apply whole sky. So it will be just a single convolution. It should be fast.
Right, but then in principle, I would need the infinite number of filters, right?
Yeah, but okay, but you can pick up some benchmark and then look.
Right. So here I was trying to keep the randomness of the signal in order to do so. But we did try that. So I don't know if so the match filter example we do is just that we don't care about the paired produced signal. We just do that for one. And then the hope is that you scan one and look at the others, you can pick up both. So for some of the examples, when the signal is brighter, we do get a good similar result. But when the signal is much dimmer, for the filtered map, we are still trying to figure out how to calculate significance using the filtered map, because there will still be lots of backgrounds around.
Yeah, I agree.
Yeah. And just CNN, it will put in some function trying to further separate the signal and background. But I totally agree, all the information that CNN can use, it should be there in match filter. Is that we need to think harder about how to dig out signal even using from the filtered map. Yeah, that's the thing I'm a bit confused about how to do it.
So regarding the inflaton scale, not the relative scales, but the absolute scale, so you get any information here about
You mean which phi
the
dot?
absolute mass, if you want?
Oh yeah, but that depends on the when this inflation happens. So that's why I show everything just as
Yeah, you show relative, yeah.
On the HI high scale, we can have 10 to the 13
I think you probably are talking about the low scale inflation.
Why is that?
Because just the phi, so your G is 1, right? G is order 1. And your mass, if it's high scale inflation, just within a couple of EFO, the delta phi is close to M-Planck. So the correction to your mass is too big. Right, so I think you're talking about low scale inflation. Epsilon is small.
Yeah, that I need to think more about this. Because
I mean, it's a general problem for particle production.
Right. Yeah, it can
the
be.
direct coupling between the inflaton and the particle usually decouples your particle pretty quickly.
Yeah, because here I'm trying to be agnostic about, like, you have a profile, like the later time is closer to the really at the central location, and I didn't really trying to predict that part, because just with the resolution, finite resolution of the signal, we usually just look at a logarithmic profile. But I agree that from a theoretical constraint, that if the correction is too big, then then we don't know what's going on in the center of the signal.
Great, let's thank Yuhsin again.